This first lab is called the gliding along lab because basically what we're going to do is we're going to take this little hover puck, which when you turn it on, it has this air that pushes down and basically it levitates on the ground. So this little hover puck is going to glide across the floor, gliding along. And the goal of this lab is to discover what constant velocity looks like, both mathematically and graphically and visually. I guess that's three things. All right. So anyway, we're going to talk about objects moving at a constant velocity. So what is constant velocity? Well, that means that the object's going to be moving at a constant speed, so going the same pace throughout the entire motion, and going a constant direction. So it's not going to be changing direction. So in order to have constant velocity, you need to have constant speed and a constant direction. So, question for you. Is this constant velocity? The answer is, yeah, pretty close. I did the best I could. So I started here, I ended over there at the same speed. I did not change direction. What about this? Is that constant velocity? Well, I went the same speed, but I changed direction, so no, it's not constant velocity. So speed and velocity are different. What about this one? What about this one? What about this one? What about this one? First try. No, that was neither constant speed nor constant velocity because it changed speed on the way up and on the way down, and it also changed direction. So this slide we're going to focus on the real basic one, constant speed and constant velocity with this little hover puck here. So let's get started. So what I'm going to do is I'm going to take this puck and I'm going to put it in this bungee cord, pull it back, and launch it this way. We're going to see what happens. So now, what I ended up doing was I launched that puck across the floor, and you notice that it went at constant velocity. Now, there might have been some spinning or some rotation involved. We're going to ignore that for now. There might have been some slight deviation side to side. We'll ignore that for now. Those are called uncertainties or small errors that we're going to talk about later. So basically what I did, when I launched it, I placed these pieces of tape down on the floor. And I marked them every single meter. So there's 1 meter, 2.00 meters, 3.00 meters, 4.00 meters, 5, 6, 7, 8, 9, 10. You get the idea. So as that puck glided across the floor, I used a timer and analyzed these videos and did several trials and figured out how long did it take the puck to travel to the 1 meter mark, to the 2 meter mark, to the 3 meter mark, etc. And I plotted that data for you here. Hey, look, back there. There's my friend the deer, Rudolph. Huh. Say hi, Rudolph. Oh, deer can't talk. So what I did is I made a data table of just the first 3 meter marks. So basically, here's what the data table looks like. The first column is displacement. So displacement is the distance from the starting point. So how far did the puck travel from 0 to 1 meters, or how far did it travel from 0 to 2 meters? So basically it's the distance from the starting point, it's displacement. And so I just did the first 3 values for you. It traveled 1.00 meters, then it traveled 2.00 meters, then it traveled 3.00 meters. And it continued on till about 10 or 11 meters is when it stopped, or when it hit the wall. I only did 3 trials. You could do much more, but I only recorded 3 trials. So for trial 1, it took the puck 0.5 seconds to get to that first meter. So from 0, let's imagine that this is the puck launching. This is the first meter mark. From 0 meters to 1 meter, it took 0.5 seconds. From 1 meter to 2 meters, so basically from 0 meters to 2 meters, this amount of time for child 1 took 1.2 seconds. Then from 0 to 3 meters, the total time it took was 2.9 seconds. So child 1, it took 0.5 seconds to get to the first meter mark, 1.2 seconds to get to the second meter mark, 2.9 to get to the third meter mark. That makes sense that those numbers got bigger and bigger because it can't go backwards in time. It didn't go backwards. It always traveled forwards, and the time kept going up. So you can kind of see that 0.5, 1.2, 2.9 is the amount of time it took for the puck to travel those different distances. Now for trial 2, the puck took 0.6 seconds to get to the first meter. Not 0.5, 0.6, so pretty close. 1.5 instead of 1.2 seconds to get to the next meter marker, and 2.6 instead of 2.9. And for the third trial, it took 0.7 seconds, 1.6 seconds, and 2.5 seconds. So that's what the markers are. So in trial 1, the time went up 0.5, 1.2, 2.9. Trial 2, 0.6, 1.5, and 2.6. And trial 3, 0.7, 1.6, and 2.5. So the time increased as the puck got farther away from the starting point, and each trial was slightly different. They were close, but not exactly the same. We're going to talk about that in the next video, part 2. We'll talk about uncertainty and what does that mean. Why are they not the same number every single time? So the next thing we're going to do, real simple, is that if I asked you a question, how much time did it take the puck to get to the first meter mark? You would all say, what? What would you say? Did it take 0.5 seconds? Well, it did the first trial, but it didn't always take 0.5 seconds. Did it take 0.6 seconds? Well, it did the second trial, but not every single trial it took 0.6 seconds. So what we want to do is average them. We want to say on average it's going to take about this much time for that puck to get to the first meter marker. So the way to find the average is we take these 3 numbers, we add them up, divide by 3. That one's pretty easy. We should get 0.6. Now, was it exactly 0.6 seconds? No, there's some error in that measurement. We're going to talk about that error with uncertainty in part 2 of this glide along lab. Okay, once again, if I were to ask you how long did it take the puck to get to the 2 meter mark, you would probably say around 1.2, 1.5, 1.6 seconds, around there. So what we could do is average those 3 numbers again, 1.2, 1.5, 1.6, average those numbers. It looks like it's 1.4. About 1.4 if I went to the 10th place. And once again, if I ask you the question, how long did it take to get to the 3 meter mark? And you would say, well, it's going to be an average of these 3 numbers, and that's about 2.6. I'll round it to 2.7. Okay, so on average, it took about 2.7 seconds to get to the 3rd meter mark. Okay. So then, what we want to do is find out, well, okay, that's average total time. On average, it took the puck 0.6 seconds, 1.4 seconds, and 2.7 seconds to get to those meter marks, so the first meter, second meter, and third meter mark. Okay, interval time. Interval time is the amount of time it takes for the puck to get from one point to the next. So the first interval, the puck traveled was from 0 meters to 1 meter. The puck traveled from its starting point to 1 meter. How much time did it take for that puck to do that? Well, it took 0.6 seconds because the timer started as soon as the puck got launched at 0 seconds. So at 0 seconds, the puck just started moving, and then at 0.6 seconds, it was at that first destination, that first interval. So basically, it's 0.6 minus 0, which is just 0.6 seconds. How long did it take the puck to get from 1 meter to 2 meter? That's what this interval is asking. Well, it was at 0.6 seconds at the 1 meter mark. It was at 1.4 seconds at the 2 meter mark. So how long did it take the puck to get to that second meter, starting from the first meter? It took 1.4 minus 0.6. That's how much time passed between those 2 meter marks, the 2 pieces of tape on the floor. That's how much time passed. If I do that math, I get 0.8 seconds. I'm going to leave some room because we'll do some uncertainty stuff next in the next video. But for right now, we're going to talk about 0.8 seconds, about. The next one, how long did it take to go from the 2 meter mark to the 3 meter mark? Well, it was at 1.4 seconds on average. Then it went to 2.7 seconds on average. So 2.7 minus 1.4 is about 1.3 seconds. So on average, it took about 0.6 seconds to travel that first meter, about 0.8 seconds to travel that second meter, and about 1.3 seconds to travel that third meter. And then we can continue for future meters along the way. That's what you're going to do for your data. Interval velocity. Interval velocity, if you look at the units for velocity, it is meters per second. So what we're going to do is take our meters that we traveled and divide it by the seconds it took to get there. What is our interval displacement divided by our interval time? So basically, how far did we travel in that interval? Well, we went from 0 meters to 1 meter. So how far did we travel? We traveled 1 meter. I'll be precise, I will say 1.00 meters. We'll talk about uncertainty later. 1.00 meters. And we're going to divide that by the interval time, which is 0.6 seconds. So when I take the interval of 1.0 meters and divide it by 0.6 seconds, I get an average of 1.7 meters per second. So in the first interval, I traveled an average of 1.7 meters in a second, all right, per second. Okay, so I want to leave some space. We'll talk about uncertainty. It's not exactly 1.7. I rounded, and also there's some uncertainty. So there's some error in each of the measurements. We'll talk about later. I can do the same thing. How far did it travel in the next interval? Well, this is kind of tricky. It didn't travel 2 meters in the next interval. It actually traveled from 1 meter to 2 meters. So the interval displacement is once again 1 meter because it traveled from 1 to 2. So it traveled 1.0 meters and it took 0.8 seconds. Nope, 0.8 seconds. So it traveled another meter in 0.8 seconds. So its average speed in that, I should say average velocity in that duration is 1 divided by 0.8, which is 1.3 meters per second. Now, once again, it's a rounded number, and there's some error in that measurement. We'll come back to that later. And finally, in that third meter marker, it traveled another meter. It traveled from 2 meters to 3 meters. That's another meter mark. So its interval displacement is 1 meter, and it traveled 1 meter in an average of 1.3 seconds. So 1 divided by 1.3 is 0.8 meters per second. So looking at this data, without even doing any further calculations or any further displacements or trials, we can see that the puck actually did not travel at constant velocity. At first it traveled 1.7 meters per second, then it traveled 1.3, and then it traveled 0.8, so it actually was slowing down. And actually that does kind of make sense that it's slowing down because there's friction on the pucks slowing it down. But there's a second reason why it might be slowing down, and that is uncertainty in our measurements. Our measurements aren't exactly right, and we rounded some numbers. So we're going to talk about what do we do with that? What sort of scenarios do we do with that going forward? So next video we'll talk about that. So what did we learn? Well, we learned that something traveling at a constant velocity is going to travel at a constant speed and a constant direction. We learned that displacement is the amount of distance from the starting point to where the ending point is. So between the starting and ending point. Interval velocity is the average velocity between 2 points, between 2 intervals. And you can find the interval velocity by taking the interval displacement and dividing by the interval time. How much distance between those 2 points and how much time did it take to get between those 2 points. And finally, we learned something about uncertainty. We didn't learn how to calculate it, but we learned that it exists and we need to consider it when dealing with measurements. So hopefully you learned something. In part 2, we're going to talk more about what to do with the next part of the lab, and hopefully I can make this shot. You know what? Count it. Say bye to Rudolph for me. Bye, Rudolph.